A circular coil carrying some current will produce a magnetic field in the region around the coil. If we are interested in the magnetic field at a point, let's say P, on an axis that passes through the center of the coil, perpendicular to its plane, a distance x from the center of the coil, the magnetic field at this point is given by this relation, where mu naught is the magnetic permeability, N is the number of turns of the coil, I is the current that passes through the coil, A is the radius of the coil, and x once again is the distance between the point and the center of the coil. B, or the magnetic field, is a vector, so it has a magnitude and direction. The magnitude is once again given by this relation. However, to find the direction, we use the right-hand rule. According to the right-hand rule, the magnetic field produced by the coil in this example is pointing to the right at the point P. The SI unit of the magnetic field is the Tesla. A special case is when the point P is at the center of the coil. In this case, the distance x is 0, so our relation will reduce to a simpler form, which is given by B equals mu naught Ni over 2A. Back to the example of our circular coil, if we can obtain an identical coil and place it on the same axis of the first coil, such that the separation between the two coils is equal to the radius of the coil, and they are connected such that they have the same current in the same direction, this setup is called the Helmholtz coils. The advantage of the Helmholtz coils is that they produce a uniform magnetic field in the region between the coils and close to the axis of the coils. The magnetic field in this region is uniform, and the magnitude of this magnetic field is given by this relation. In part 1 of our experiment, the magnetic field as a function of x will be demonstrated. In part 2 of the experiment, your instructor will demonstrate the Helmholtz coils for you and will show you how the magnetic field between the two coils is uniform, close to the axis of the coils. Your work starts in part 3, where you will get a circular coil and you will place a magnetic field sensor at x equals 0, in other words at the center of the coil. Then by passing a variable current in the coil, you'll be studying the current versus magnetic field. A graph of B versus I will be obtained, and you will use your knowledge of the relation B equals mu naught Ni over 2A to calculate the magnetic permeability experimentally. This is the setup for this experiment. We have the magnetic field sensor right here, which is attached to a rotary motion sensor. The purpose of this sensor is to measure the position of the magnetic field sensor. So we have the magnetic field sensor attached via this string, which is kept tight by hanging a mass down there. Okay. Now if I move the magnetic field sensor, notice how the rotary motion sensor is going to rotate, and this will record the position of the magnetic field sensor. Now all of the setup is mounted on this stage that we can move left and right. Okay, and notice how when I move it, the magnetic field sensor will pass through the coil. Okay, this is how we can get the position versus magnetic field strength. So the magnetic field sensor will record the magnetic field strength, and the rotary motion sensor will record the position of the magnetic field sensor. Okay. This is the magnetic field sensor that we use for this experiment. This setting allows us to measure the magnetic field that goes directly into the axis of the sensor entering this dot. This setting allows us to measure the magnetic field sensor component, or the magnetic field component that enters into the side of the sensor. This is how you can reset the sensor. And this is to specify the range that we're interested in. Okay, so for our purpose, we're gonna keep it on the axial mode, which measures the magnetic field in this direction. Okay. The two coils have to be connected so that the current flows in them in the same direction in both of them. So this terminal number 1 is connected to terminal number 2, and so on. This one goes back to the power supply. Let's just extend the wire. Okay, now the distance between the two coils from here, I'm measuring from the front surface. This distance should be equal to the radius of each coil. This combination, we call it the Helmholtz coil combination. Let's make sure they are parallel and they are exactly at 1 radius separation from each other. Okay, so the radius again is equal to the distance between the two coils. Alright, now the sensor is moving close to the coil, so the magnetic field is increasing. Now, in the area between the two coils, notice how the magnetic field is almost constant at a straight line, horizontal line. And then now, after that, after it passes the second coil, starts to decrease again. Okay, I will repeat it quickly. So you see a smooth curve. All right.